dawn of differential calculus. From a modern perspective, there are two sides to calculus. Differential calculus cuts complicated problems into infinitely many simpler pieces. Integral calculus puts the pieces back together again to solve the original problem. Given that cutting comes naturally before rebuilding, it seems sensible from a novice to learn differential calculus first, and indeed, that's how all calculus courses begin today. They start with derivatives, the relatively easy techniques for slicing and dicing, and then work their way up to integrals, the much harder techniques for reassembling the pieces into an integrated whole. Students find it more comfortable to learn calculus in this order because the easy material comes first. The teachers like it because the subject seems more logical this way. Yet, strangely enough, history unfolded in the opposite order. Integrals were already in full swing in ancient Greece in Archimedes' work around 250 BCE, whereas derivatives weren't even a gleam in anybody's eyes until 1600s. Why did differential calculus, the sheer side of the subject, develop so much later than integral calculus? It's because differential calculus grew out of algebra, and algebra took centuries to mature, migrate, and mutate. In its original form in China, India, and the Islamic world, algebra was entirely verbal. Unknowns were words, not today's unknowns were words, not today's X and Y. Equations were sentences, and problems were paragraphs. But soon after algebra arrived in Europe, around 1200, it evolved into an art of symbols. That made algebra more abstract and more powerful. This new breed, symbol algebra, that coupled with geometry and spawned an even stronger hybrid, analytical geometry, in which in turn begat a zoo of new curves, the study of which led to the way to differential calculus. This chapter explores how that happened. The rise of algebra in the East. The mention of China, India, and the Islamic world should correct the impression I may have given so far that the creation of calculus was a recent affair. Although calculus culminated in Europe, its roots lie elsewhere. In particular, algebra came from Asia and Middle East. Its name derives from the Arabic word al-jabr, meaning restoration or the reunion of broken parts. These are the kinds of operations needed to balance equations and solve them, for instance by subtracting a number from one side of an equation and adding it to the other, in effect restoring what was broken. Likewise, geometry, as we've seen, was born in ancient Egypt, the founding father of Greek geometry. Thales is said to have learned the subject there, and the greatest theory of geometry, the Pythagorean Theorem, did not originate with Pythagoras. It was known to the Babylonians for at least 1,000 years before him, and evidenced by examples of it on Mesopotamian clay tablets from around 1800 BC. We should also keep in mind that we speak of ancient Greece, we are referring to whose watch of territory that reached far beyond Athens and Sparta. At its largest, it stretched to Egypt in the south, to Italy and Sicily in the west, and is across the south of Mediterranean to Turkey, the Middle East, Central Asia, and parts of Pakistan and India. Pythagoras himself was from Samos, an island of the coast. There was coast of Asia Minor, now Turkey. Archimedes lived in Syracuse, on the southern coast of Sicily. Evclid worked in Alexandria, the Greek port, a scholarly hub at the mouth of the Nile in Egypt. After the Romans conquered the Greeks, and especially after the library in Alexandria was burned, and the Western Roman Empire fell, the center of mathematics swung back to the east. The, the writings of Archimedes and Euclid were translated into Arabic, as were those of Ptolemy, Aristotle, and Plato. Scholars and scribes in Constantinople and Baghdad keep the old learning alive and added ideas of their own. How algebra works while geometry won. During those centuries before algebra arrived, geometry slowed to a crawl. After Archimedes died in 212 BCE, it seemed that nobody could beat him at his own game. Well, almost nobody. Around 250 BCE, the Chinese geometer Liu Hui improved on Archimedes' method for calculating pi. 2 centuries later, Su Zongxi applied Liu Hui's method to a polygon with 24,578 sides. Through what must have been heroic feats of arithmetic, he tightened the size on pi to 8 digits. The next step forward took another 5 centuries and came from the sage Al-Hasan ibn al-Haytham, known to Europeans Al-Hasan, born in Basra, Iraq, around 965 BCE. He worked in Cairo during the Islamic Golden Age on everything from theology and philosophy to astronomy and medicine. In his work on geometry, Ibn al-Haytham calculated volumes of solids that Archimedes never considered. Still, impressive as these advances were, they were rare signs of life for geometry, and they took 12 centuries to occur. During that same long span of time, rapid and substantial advances were being made in algebra and arithmetic. Hindu mathematicians invented the concepts of zero and the decimal placed value system for numbers. Algebraic techniques for solving equations sprang in Egypt, Iraq, Persia, and China. Much of this was driven by practical problems involving inheritance law, tax assessment, commerce, bookkeeping, interest calculations, and other topics well suited to numbers and equations. In those days, when algebra was still all about word problems, solutions were given as receipts, step-by-step routes to answers, as elucidated in the famous textbook by Muhammad ibn Musa al-Kharizmi circa 780 until 850 CE, whose last name lives on in the step-by-step procedures called algorithms. Eventually, traders, merchants, and explorers brought this verbal form of algebra in Hindu-Arabic decimals westward to Europe. Meanwhile, people started translating Arabic text into Latin. The study of algebra in its own right, as a symbolic system apart from its applications, began to flourish in Renaissance Europe. It reached its pinnacle in 1500s, when it started to look like what we know today, with letters used to represent numbers. In France, in 1591, Van Corviet designated unknown quantities with vowels like A and E and used consonants like B and G for constants. Today's use of XYZ for unknowns and ABC for constants came from the work of René Descartes about 50 years later. Replacing words with letter and symbol made it much easier to manipulate equations and find solutions. An equally big advance in the realm of arithmetic came when Simon Stevin in Holland sought how to generalize Indo-Arabic decimal numbers to decimal fractions. In so doing, he destroyed the old Aristotelian distinction between numbers, meaning whole numbers of indivisible units, and magnitudes, continuous quantities that could be divided infinitely into arbitrarily small parts. Before Stevin, decimals had been applied only to the whole number part of quantity, and at any part less than a unit was expressed as a fraction. In Stevin's new approach, even a unit could be chopped into pieces and written in decimal notation by placing the correct digits after the decimal point. It sounds simple to us now, but it was a revolutionary idea that helped make calculus possible. Once the unit was no longer sacrosanct and indivisible, all quantities, whole, fractional, and irrational, coalesced into one big family of numbers, all on equal footing. That gave calculus the infinitely precise real numbers it needed to describe the continuity of space, time, and motion and change. Just before geometry patterned with algebra, there was one la- there was one last hurrah for the old school geometric methods of Archimedes. At the beginning of the 17th century, Kepler found the volumes of curved shapes like wine barrels and donut-shaped solid by slicing them, in his mind, into an infinite number of infinitesimally dense disks. When Galileo and his students Evangelista Torricelli and Bonaventura Cavalieri similarly computed areas, volumes, and centers of gravity of various shapes by treating them as infinite stacks of lines and surfaces. Because these men had a devil-may-care approach to infinity and infinitesimals, their techniques were not rigorous, but then but they were potent and intuitive. They they, pros- they produce answers like much more easily and quickly than the method of exhaustion. So this seemed like an exciting advance, though we know how the Archimedes had beaten them to it. There's some idea lay hidden in his treatise on the method that all at the time still languishing undetected in a prayer book in a monastery, where it would remain until 16, 18, 18 until 1899. At any rate, although the progress made by the neo by made the new Archimedean by the neo Archimedeans seemed promising at the time, its continuation of the old approach was not destined to carry the day. Symbolic algebra was now where the action was, and with it, the seeds for its most rigorous offshoots, analytic geometry and differential calculus, were finally about to be sown. Algebra meets geometry. The first breakthrough came around 1630 when two French mathematicians and soon-to-be rivals, Pierre de Fermat and René Descartes, independently linked algebra to geometry. Their work created a new kind of mathematics, analytic geometry, whose central theater was the xy plane, an arena where equations came alive and took form. We use the xy plane today to graph relationships between variables. For example, consider the caloric implications of my occasionally disgraceful eating habits. Sometimes I treat myself to a couple of slices of cinnamon raisin bread for breakfast. On the package, it tells me that each slice, each slice packs a whopping 200 calories. If I wanted to eat healthier, I could always settle for the 7-grain bread my wife buys with its 130 calories per slice. But for this example, I prefer the cinnamon raisin bread because 200 is more congenial number. mathematically is not nutritionally than 130. Here's a graph of many calories I consume and I weigh when I eat 1, 2, or 3 slices of bread. Since its slice amounts to 200 calories, 2 slices amount for 400 calories, and 3 to 600 calories. When plotted as data points on the graph, all 3 points, fall on the same straight line. In that sense, there's a linear relationship between calories consumed and number of slices eaten. If we use the letter x to represent the number of slices eaten and y for the number of sinful calories ingested, the linear relationship can be summarized as y equals to 100x. This relationship also applies between the data points. For example, 1½ slices amount to 30 calories, and the corresponding data points falls on the line. So it makes sense to connect the dots in graphs like this. I realize all of this might seem obvious. That's my point. It was not always obvious. It was not obvious in the past. Someone had to come up with the idea to depict relationships on an abstract visual chart, and it still is not obvious today. At least no, at least not to kids when they first learn about graphs like this. There are several imaginative leaps here. One is to use a picture to represent food intake that requires mental flexibility. There is nothing inherently pictorial about calories. The graph we're looking at is not a photorealistic painting showing raisins and brown swirls of cinnamon embedded in the bread. The graph is an abstraction. It allows different mathematical domains to interact and cooperate. The domain of numbers, like numbers of calories, of size of bread, the domain of symbolic relationships like y equal to 100x, and the domain of shapes like dots lying on a straight line on a graph within two perpendicular axes. Through the confluence of ideas, the humble chart blends numbers, relationships, and shapes, and hence lets arithmetic and algebra merge into geometry. That's the big deal here. Different streams of mathematics have been brought together after centuries of running on their separate courses. Recall that the ancient Greeks elevated geometry over arithmetic and algebra and did not let them mingle, at least not very often. Another confluence here involves the horizontal and vertical axes. They are often called the x and y axes, named for the variable used to label them. These axes are number lines. Think about them. Number lines. Numbers are being represented as a point on the line. Arithmetic is constructing with geometry, and they are mingling before we even plot any data. The ancient Greeks would have screamed bloody murder at, at that breach of protocol. To them, numbers mean exclusively discrete quantities like whole numbers and fractions. By contrast, continuous quantities of the sort measured by the length of a line were regarded as magnitudes, a conceptual distinct category from numbers. So, for nearly 2000 years from Archimedes to the beginning of the 17th century, numbers were absolutely not seen as equivalently to continuum of points on a line. In this sense, the idea of number line was radically transgressive. Nowadays, we don't give it a second thought. We expect elementary school children to understand that numbers can be represented visually in this way. Further blasphemy here, from the standpoint of the ancient Greeks, is the graphs are disregarded for comparing like with like, apples with apples, or calories with calories. Instead, the graph shows calories on one axis and slices on the other. They are not directly comparable, and yet we don't blink an eye at making such comparisons today when we draw graphs like this. We simply convert calories and slices to numbers, meaning real numbers, infinite decimals, the universal currency of continuous mathematics. The Greeks drew sharp distinctions between lengths, areas, and volumes, but they are all just real numbers to us. Equations as curves. To be sure, Fermat and Descartes never used the xy plane to study anything as tangible as cinnamon raisin bread. For them, the xy plane was a tool to study pure geometry. Working separately, they each noticed that any linear equation, meaning an equation in which x and y appear to the first power only, produced a straight line on the xy plane. This connection between linear equations and lines suggested the possibility of a deeper connection, one between nonlinear equations and curves. In a linear equation like y equals 200x, the variables x and y appear on their own unaltered and do not get squared or cubed or raised to any higher power. Fermat and Descartes realized they could play the same game with other powers and other questions. They could cook up any equation they desired and do whatever they wanted to x and y, square one of them, cube the other, multiply them together, add them, whatever, and then interpret the result as a curve. With any luck, it would be an interesting curve, maybe one that nobody had ever imagined, maybe one that Archimedes had never studied. Any equation with x and y in it, with y and xy with x and y in it, was a new adventure. It was also a gestalt switch. Instead of starting with a curve, you start with an equation and see what kind of curve it makes. Let algebra drive and put geometry in the back seat. Fermat and Descartes began by looking at quadratic equations. These are equations in which, along with usual constants like 200 and linear terms like x and y, the variables can also get squared or multiplied together, creating quadratic terms like x squared, y squared, and xy. In Latin, quadratus means square. Squared quantities had traditionally been interpreted as the areas of square regions. Thus, x squared means the area of an x by x squared. In the old days, an area was seen as a fundamentally different kind of quantity from a length of a volume. But to Fermat and Descartes, x squared was just another real number, which meant it could be graphed on a number line just as x or x cubed or any other power of x could be. Today, students in high school Today, students in high school algebra are routinely expected to be able to graph equations like y equal x squared, whose associated curve turns out to be a parabola. Remarkably, all other questions involving quadratic terms in x and y, but no higher powers, give curves of just four possible types: parabolas, ellipses, hyperbolas, or cycles. and that's it, except for some degenerate cases that yield lines, points, or no graph at all, but these are rarely oddities that we can safely ignore. For example, the quadratic equation xy equals 1 give uh, give us a hyperbola uh, give us give a hyperbola, while x squared plus x squared equals 4 is a cycle, and x squared plus 2 squared equals 4 is an ellipse. Even a quadratic as basely as x squared plus 2xy plus plus y squared plus x plus 3y equals 2 has to be one of the four possibilities above. It turns out to be a parabola. Fermat and Descartes were the first to discover this wonderful coincidence. The quadratic equations in x and y are the algebraic counterparts of the conic sections of, of the Greeks, the four kinds of curves obtained by slicing through a cone at different angles. Here, in Fermat's and Descartes' new arena, classical curves were reappearing like ghosts from the mist. Better together. The newfound ties between algebra and geometry were a boon to both subjects. Each could help the other compensate for its deficits. Geometry appealed to the right side of the brain. It was intuitive and visual, and the truth of its propositions were often clear at a glance. But it called for a certain kind of inequality, ingenuity. With geometry, there was often no clue about where to start a proof. Beginning an argument required strokes of genius. Algebra, however, was systematic. Equations could be massaged almost mindlessly, peacefully. You could add the same term to both sides of an equation, cancel common terms, solve for an unknown quantity, or perform a dozen other procedures and algorithms according to standard recipes. The process of algebra could be soothingly repetitive, like the pleasures of knitting, but algebra suffered from its emptiness. Its symbols were focused. They mean nothing until they were given meaning. There was nothing to visualize. Algebra was left-brained and mechanical. Together, too, algebra and geometry were unstoppable. Algebra gave geometry a system. Instead of needing ingenuity, it now demanded tenacity. It transformed difficult questions requiring insight into straightforward, if laborious, calculations. The use of symbols freed the mind and saved time and energy. For its part, geometry gave algebra meaning. Equations were no longer sterile. They were now embodiments of sinus geometric forms. A whole new continent of curves and surfaces opened up as soon as equations were viewed geometrically. Lost jangles of geometric flora and fauna waited to be discovered, catalogued, classified, and dissected. Fermat versus Descartes. Anyone who has studied a lot of math and physics will have run into the names of Fermat and Descartes, but none of my teachers of textbook ever taught me about their rivalry or how vicious Descartes could be. To understand what was at stake in their fights, you need to know more about their life, their personalities, and what they hoped to achieve. René Descartes, 15, 1596 until 1650, was one of the most ambitious thinkers of all time, daring, intellectually fearless, and contemptuous of authority, he had an ego as big as his genius. For example, of the approach to geometry, which all other mathematicians had revered for 2,000 years, he wrote dismissively, "What the science have taught us is so scanty and for the most part so lacking in credibility that I might hope for any kind of approach toward truth except by rejecting all the paths which they had followed." At a personal level, he could be paranoid and thin-skinned. The most famous portrait of him shows a man with gaunt face, haughty eyes, and snide little mustache. He looks like a cartoon villain. Descartes set out to rebuild human knowledge on a foundation of reason, science, and skepticism. He is best known for his work in philosophy, immortalist for his famous like "Cogito ergo sum", I think, therefore I am. In other words, when all when all is in doubt, at least one thing is certain: the doubting mind exists. His analytic approach, which appears to have been inspired by the rigorous logic of mathematics, is widely seen today as the beginning of modern philosophy. In his most famous book, his discourse on method, Descartes introduced a bracing new style of thinking about philosophical problems, but he also included the three appendices of interest in their own right: one on geometry, in which he presented his approach to analytic geometry; another on optics, and of great import at the time of when telescopes, microscopes, and lenses were the latest technology; and a third of weather, which has mostly been forgotten except for his correct explanation of rainbows. His capacious intellect roamed far and wide. He viewed the living body as a system of mechanical devices, and located the seat of the soul in the brain pineal gland. He proposed a grand, but wrong, system of the universe according to which invisible vortices pervaded all space, with the planets carried along like leaves in a whirlpool. Born into a wealthy family, Descartes was sickly as a little boy and was allowed to stay in bed and read and think as long as he liked, a habit he kept his whole life, never rising before noon. His mother died when he was just a year old, but fortunately she left a sizable inheritance that later allowed him to alive to his mother died when he was just a year old, but fortunately she left him a sizable inheritance that later allowed him to live a life of leisure and adventure as a wandering gentleman. He volunteered for the Dutch army but never saw combat, and he had plenty of time for philosophy. He spent much of his adult life in Holland, working on his ideas and corresponding and bickering with other great thinkers. In, si- in 1650, in 1650, he reluctantly took a position in Sweden, which is known as the which is known as country of bears, amid rocks and ice, as Queen Christina's personal philosophy tutor. Unfortunately for Descartes, the energetic young queen was an early riser. She insisted on lessons at 5 in the morning, an godly hour for anyone but especially for Descartes, as accustomed to getting up at the noon his whole life. That winter in Stockholm was the coldest in decades. After a few weeks, Descartes caught, caught pneumonia and died. Pierre de Fermat, 1601 until 1601 until 1665, who was 5 years younger than Descartes, lived a peaceful, upper middle class, comparatively uneventful life. By day, he was a lawyer and provincial judge in Toulouse, far from the hub in Paris. By night he was a husband and father. He come home from work at dinner with his wife and five kids, and then spent a few hours with his one true passion, doing math. Whereas Descartes was a big thinker of colossal ambitions, Fermat was a Simon, quiet, even-tempered, and naive. He had more modest goals than Descartes did. He didn't see himself as a philosopher or a scientist. Math was enough for him. He pursued it as an amateur lovingly. He saw no need to publish, and he didn't. He wrote little notes to him in the books he was reading, classic Greek, classic Greeks, classic Greek tomes by Diophantus and Archimedes, and occasionally mailed his ideas to scholars he thought might appreciate them. He never traveled far from Toulouse or met any of major mathematicians of his day, although he corresponded with them through Marie Mersenne, a Franciscan friar, mathematician and social connector. It was through Mersenne that Fermat and Descartes locked horns. Among mathematicians, Mersenne was the go-to guy in Paris. In a in a time before Facebook, he kept everyone in touch with everyone else. A real busybody with a certain lack of tact and discretion. He had a way of stirring up trouble. For example, he sought people personal letters he received and released confidential manuscripts before they were published. There was a cycle around him of top mathematicians, not quite in the same leagues as Fermat and Descartes, but strong, no, but strong nonetheless, and they apparently had it in for Descartes. They were always snipping at him and his grandiose discourse on method. So, when Descartes had via Mersenne that some nobody in Toulouse, some amateur named Fermat, claimed to have developed analytic geometry at Descartes earlier than he had, and that this some amateur, who was this guy, has raised doubts about his theory of optics. Descartes considered it another case of someone out to get him. In the year to come, he fought vehemently against Fermat and tried to ruin his reputation. After all, Descartes had a lot to lose. In discourse, he claimed that his analytical method was the one so good to knowledge. If Fermat could outdo him without even using his method, his whole project was at risk. Descartes, but most Fermat, mercilessly and to some extent succeed in diminishing him. Fermat's work was never properly published until 1679. His result trickled out through word of mouth or in copies of his letters, but he was not truly appreciated until long after his death. Descartes, however, hit it big. His discourse became famous. The next generation learned analytic geometry from it. Even today, our students learn about Cartesian coordinates, even though Fermat came up with them first. The search of analysis, the long-lost method of discovery, the scribbles between Descartes and Fermat, took place against the backdrop of the early 17th century, a time when mathematicians dreamed of finding a method of analysis for geometry. Here, analysis, as in analytic geometry, is to be understood in the archaic sense of the word, as a means of discovering results rather than providing them. There was widespread suspicion at the time that the ancients had possessed such a method of discovery but had deliberately concealed it. Descartes, for example, alleged that the ancient Greeks had knowledge of a species of mathematics very different from that which passes current in our time. But my opinion is that this written then with a sort of low cunning, deplorable indeed, suppress this knowledge. Symbolic algebra seemed like it might be this long-lost method of discovery, but in more conservative quarters, with algebra met with reactionary skepticism a generation later, when Isaac Newton said algebra is the analysis of the bunglers in mathematics. He was drawing a thinly veiled insult at Descartes, a prime example of a bungler who had relied on algebra as a crutch to solve problems by working backward. In launching his attack, Newton was adhering to a traditional distinction between analysis and synthesis. In analysis, one solves a problem by starting at the end as if the answer had already been obtained and then walks back wistfully toward the beginning, hoping to find a path to the given assumptions. It's what kids in school think of as working backward from the answer to figure out how to get there. Synthesis goes in the other direction. It starts with the givens, and then, by standing in the dark, trying things, you are somehow supposed to move forward to a solution step by logical step, and eventually arrive at the desired result. Synthesis tends to be much harder than analysis because you don't ever know you are going to get to the solution until you do. The ancient Greeks regarded synthesis as carrying more logical force, more persuasive power than analysis. Synthesis was considered the only valid way to prove a result. Analysis was a practical way to find the result. If you wanted a rigorous demonstration, you had to do synthesis. That's why, for example, Archimedes used his analytical method for balancing sets of seesaws to find his theorems, but then switched to the synthetic method of exhaustion to prove them. Still, although Newton looked down his nose at algebraic analysis, we will see in chapter 7 that he used it himself and tremendous effect. But he was not its first master. Fermat was. Fermat's style of thinking is fun to examine because it's elegant and accessible and yet foreign and surprising. His methods for studying curves are no longer in use, having been superseded by the more sophisticated techniques in the textbooks today. Optimizing for the overhead bin. Fermat embryonic version of differential calculus grew out of his application of algebra to optimization problems. Optimization is the study of how to do things in the best possible way. Depending on context, best might mean fastest, cheapest, biggest, more profitable, more efficient, or some other notion of optimality. To illustrate his ideas in a simple fashion, Fermat contrived here a few problems that sound a lot like the exercises we math teachers are still assigning to our students today. They can blame it all him. On those problems, updated for our time, goes something like this. Imagine you want to design a rectangular box to hold as much stuff as possible, subject to two constraints. First, the box has to have a square cross-section, x inches wide and y inches and x inches deep. Second, it has to fit the overhead bin of a certain airline. According to the rules of carrying on baggage, the width plus depth plus height of the box cannot exceed 45 inches. What choice of x produce a box of maximum volume? One way to solve this is with common sense. Try a few possibilities. Say the width and depth are 10 inches each. That would allow for a height of 25 inches, since 10 plus 10 plus 25 equals 45. A box with those dimensions would have a volume of 10 times 10 times 25, which equals to 2,500 cubic inches. Would a cube-shaped box be better? Since a cube must have equal height, width, and depth, it would have to have a dimension 15 times 15 times 15, which multiplies out to a roomy 3,375 cubic inches. Fiddling around with a few other possibilities makes it seem likely that a cube is the optimal choice for the shape of the box, and indeed it is. So this is not particularly hard problem in itself. The point of view, the point of it is so to how Fermat reasoned about such problems, because his approach led to much greater things. As in most algebra problems, the first step is to translate all the given information into symbols. Since the width and depth of the box are both x, they add up to 2x. Since the height plus width plus depth cannot exceed 45 inches, that leaves 45 minus 2x for the height. Thus the volume will be x times 45 minus 2x. Multiplying that out gives 45x squared minus 2x cubed. That's the volume of our box. Call it Vx. Thus, Vx equals 45x squared minus 2x cubed. If we check momentarily and use a computer of graphing calculator to plot x horizontally and xv vertically, we see that the cube rises up and reaches its maximum when x equals 15 inches as expected, and then descends back to 0. Alternatively, to find that maximum differential calculus as practiced today, our students will reflexively take the derivative of v and set it equal to 0. The thinking is that at the top of the curve, the slope is 0. The curve is neither rising nor falling there. So, since the slope is measured by the derivative, as we'll see in chapter 6, the derivative must be 0 at the maximum. After a bit of algebra and the incantation of various memorized rules for derivatives, this line of reasoning will also lead x times x equals 15 at the maximum. But Fermat didn't have graphical calculators or computers, and he certainly didn't have the concept of derivatives. On the contrary, he invented the idea that led to derivatives. So how did he solve the problem? He used a special property of the maximum. Horizontal lines below the maximum intersect the curve at 2 points as shown here, whereas horizontal lines above the maximum do not intersect the curve at all. That suggested an intuitive strategy to solve the problem. Imagine slowly lifting a horizontal line that starts below the maximum. As the line gradually moves up, its two intersection points slide toward each other along the curve like beads on a necklace. At the maximum, those 2 points collide. Looking for that collision was how Fermat determined the maximum. He derived a condition for 2 points to merge into one, forming what's known as a double intersection. With that insight in place, the rest is algebra, the mere manipulation of symbols. It goes as follows. Say the two intersections occur at x equals a and x equals b. Then, since by construction they lie on the same horizontal line, we must have VA equals VB. Hence, 45x squared minus 2a cubed equals 45b squared minus 2b cubed. To make headway, it helps to rearrange this equation. If we put the squares on one side and the cube on the other, we get 45x squared minus 45b squared equals 2a cubed minus 2b cubed. With some skill in high school algebra, we can then factor both sides to obtain 45 a minus b, a plus b, 2 a minus b, a squared plus ab plus b squared. Next, divide both sides by the common factor of a minus b. That's legal since a and b are assumed to be different. If they were equal, dividing both sides by a minus b would amount to dividing by 0, which is prohibited as discussed in Chapter 1. After cancellation, the resulting equation is 45a plus b equals 2a squared plus ab plus b squared. Buckle up now for a confusing point of logic. Fermat has just assumed that a and b are not equal, yet he goes on to imagine that the equation he has just derived will continue to hold when a and b do become equal as they max at the maximum. He tries to justify this by invoking a murky concept he calls adequately. It expresses the idea that a and b become sort of equal, but not really equal at the maximum. Today, we will praise it using the concept of a limit or a double intersection. Anyway, he says a approximate b when the squiggly equals signs means equal, and then Cavalieri substitutes a for b in the equation above to get 45 2a equals 2a squared plus a squared plus a squared. This simplifies to 90a equals 6a squared, whose solutions are a equals 0 and a equals 15. The first of these solutions, a equals 0, gives a box of minimum volume. It has 0 width and depth and hence has 0 volume. That's of no interest. The second solution, a equals 15, the box of maximum volume. That's the answer we've been expecting. 15 inches is the optimal width and depth. From today's perspective, Fermat reasoning seems strange. He finds a maximum without using derivative. Today we teach derivatives before we optimization. Fermat did it the other way around, but it does not matter. His ideas are equivalent to ours. How Fermat helped the FBI. The legacy of Fermat's early work on optimization is all around us. Our lives today depend on algorithms that solve optimization problems using the notion of double intersections and equivalent conditions expressed with derivatives. Today's problems tend to be much more complicated than Fermat's, but their spirit is the same. One important application involves big data sets, where it's often helpful to code the data as compactly as possible. For example, the Federal Bureau of Investigation has millions of records of fingerprints. To store them, search them, and retrieve them efficiently for background checks, they use calculus-based method of data compression. Clever algorithms reduce the size of the digitized fingerprint files without sacrificing any details that matter. The same is true when you store music and pictures on your phone. Rather than keep every note and pixel, compression algorithms name MP3 and JPEG save space by distilling the information down to a much more efficient form. They also let us download songs and photos quickly and send them to our loved ones without clogging up their inboxes too much. To see what calculus and optimization have to do with data compression, let's take a look at the related statistical problem of fitting a curve to data, an issue that comes up everywhere from climate science to business forecasting. The data set we'll examine shows how the length varies with the seasons. As we all know, the days are longer in the summer and shorter in the winter. What does the overall pattern look like? In the graph below, I've plotted the data for New York City for the year 2018, with time running horizontally from January 1 on the far left on December 31 on the far right. The vertical axis shows the number of minutes between sunrise and sunset at different times of the year. To avoid cluttering up the picture, I found the data for only 27 days, sampled every 2 weeks starting on January 1. The graph shows the data length rises and falls throughout the years. Throughout the year, as expected, the days are longest around the summer solstice, June June 21, corresponding to the peak at 172 near the middle of the graph, and shortest around the winter solstice. Of a year later, overall, the data appear to lie on a smoothly undulating wave. In high school trigonometry cases, teachers talk about a certain kind of wave, a sine wave. Later in this book, I will have more to say about what sine waves are and why they are special from the standpoint of calculus. For now, the main thing we need to know is that sine waves are connected into circular motion. To see the connection, imagine a point moving around a cycle at a constant speed. If we track its up and down position as a function of time, the point traces out a sine wave. And because cycles are intimately connected to cycles, sine waves come up wherever cycle phenomena occur, from the cycle of the seasons to the vibrations of tuning fork to the 60 cycle hum of fluorescence like and power lines. That annoying hum is the sound of sine waves bobbing up and down 60 times a second. It's the telltale sign of alternating current produced by generators, the power of grid whose machinery is spinning at the same frequency. Where there is circular motion, there are sine waves. Any sine wave is completely defined by orbital statistics, its period, average, amplitude, and phase. These four parameters have simple interpretation. The period T indicates how long it takes the wave to complete a full cycle. For the day length data, we're considering here. T is about a year off. To be more precise, 300 365.25 days. That extra quarter of a day is why we need a leap years for every fourth year to keep the calendar in sync with natural cycles. The average of the sine wave is its baseline value, B. For our data, it's the typical number of minutes of daylight in New York City average across all the days of the year 2018. The wave's amplitude A tells us how many additional minutes of light there are on the longest day of the of the of the year compared to the average days. The wave base C tells us the day on which the wave causes upward to its average value sometime around the spring equinox. It's helpful to think of these four parameters A, B, C, T as four knobs we can turn to adjust various thetas of the sine wave's shape and location. The B knob moves the sine wave up and down. The C knob moves it left or right. The T knob controls how rapidly it oscillates. The A knob determines how pronounced those oscillations are. If we could somehow set the knobs to make the sine wave go to all the data points we plotted earlier, that would amount to a significant compression of information. It would mean we were capturing the 27 data points with just the 4 parameters in the sine wave, thereby compressing the data by a factor of 27 over 4 or 60.75. Actually, since we know one of the parameters is a year, we really have only 3 parameters to fiddle with, giving us a compression giving us a compression factor of 27 over 3 or 9. A reduction of this size is conceivable because the data are not random. They follow a pattern. The sine wave embodies the pattern and does the work for us. The only catch is that there is no sine wave that goes through the data perfectly. That's to be expected when fitting an idealistic model to real-world data. There are bound to be some discrepancies. The hope is that the discrepancies are negligible. To minimize them, we need to find the sine wave that hugs the data points as closely as possible. That's where calculus comes in. The figure below shows the best fitting sine wave as determined by an optimization algorithm I'll explain in a minute. But first, notice the resulting fit is not perfect. For instance, the wave does not quite dip down low enough in December when the days are very short and the data fall below the curve. Nevertheless, a simple sine wave certainly captures the sense of what's going on. Depending on our goals, a fit of this quality may be adequate. How does calculus come in? It helps us choose the 4 parameters optimally. Imagine turning the 4 knobs to get the best possible fit, somewhat like turning the dial of a radio to get the strongest possible signal. This is essentially what Fermat did in the overhead bin problem, when he found the roomiest dimensions for the box. In that case, he was turning a single parameter x, the side length of the box, and looking for double intersection as a signal that the volume of the box was a maximum. In our case, we have four parameters to tune, but the basic idea is the same. We'll look for a double intersection, and that will give us our optimal choice of the 4 parameters. In a little more detail, here's how it works. For any given choice of the four parameters, we calculate the discrepancy, in other words the error between the since wave fit and the actual data at every one of the 27 points recorded to the year. A natural criterion for choosing the best fit is that the total error summed over all 27 points should be as small as we can make it. But total error is not quite the correct concept because we don't want the negative errors to cancel the positive ones and give the false impression that the fit has less error than it does. Undershoots are just as bad as overshoots, and both should be penalized. They should be allowed to cancel out. For this reason, mathematicians square the errors at each point to make the negative ones become positive. That's why they can't possibly produce any spurious cancellation. Here's one place Here's one place where the fact that a negative times a negative is a positive is useful in practical setting. It makes the square of a negative error count as a positive discrepancy as it should. So, the basic idea is to choose the four parameters in the sine wave in such a way that they minimize the total square error of the fit to the data. Accordingly, this approach is called the method of least squares. It works best when the data follow a pattern as they do here, all of which raises an extremely important general point. Patterns are what make compression possible in the first place. Other pattern data can be compressed. Random data cannot. Happily, many of the things people care about it, like songs and faces and fingerprints, are highly cluttered and patterned. Just as the length follows a simple wave pattern, a photograph of a face contains eyebrows, blemishes, cheekbones, and other characteristic patterns. Songs have melodies and harmonies, rhythms and dynamics. Fingerprints contain ridges and loops and woes. As human beings, we recognize these patterns instantly. Computers can be taught to recognize them too. The trick is to find the right kinds of mathematical objects to encode particular patterns. Sine waves are ideal for representing periodic patterns, but they are less well suited to presenting sharply localized features like the edge of a nostril of a beauty mark. For this purpose, researchers in several different fields came up with a generalization of sine waves called wavelets. These little waves are more localized than sine waves. Instead of extending periodically out to infinity in both directions, they are sharply concentrated in time or space. Wavelets suddenly turn on, oscillate for a while, and then turn off. They look almost like the signals on heart monitors or the bursts of activity recorded on seismograph during an earthquake. They are ideal for representing a sudden spike in brainwave recording, a bird stroke on a Van Gogh painting, or a wrinkle on a face. The Federal Bureau of Investigation used wavelets to modernize their fingerprint files. From the time fingerprints were introduced at the beginning of 20th century, fingerprint records had been stored as ink impressions or on paper cards. The files were difficult to search quickly. By the mid-1990s, the collections had grown to roughly 200 million fingerprint cards on file and occupied an acre of office space. When the FBI decided to digitize the files, they turned them into grayscale images with 256 different levels of gray at a resolution of 500 dots per inch, enough to capture all the fine whorls, loops, ridge endings, bifurcations, and other identifying minutiae of fingerprints. The problem, however, was that at the time, a single digitized card contained about 10 megabytes of data. That made, that made it prohibitive for the FBI to send digital files quickly to local police. Remember, this was in the mid 1990s when phone modems and fax machines were state of the art, and transmitting of 10 megabyte file took hours. Plus, it was tough to exchange files that big when 1.5 megabytes floppy disk when the medium of choice. Given the growing demand for faster turnaround times on the 30,000 new fingerprint cards that flooded in every day with urgent requests for background checks, there was a desperate need to modernize the system. The FBI had to find a way to compress the files without distorting them. Wavelets were ideal for the job by representing fingerprints as combinations of many wavelets and by turning the knobs on them optimally using calculus. Mathematicians from the Los Alamos National Lab teamed up with the FBI to shrink the files by a factor of more than 20. It was a revolution of forensics. Thanks to Fermat's ideas in their modern form, along with an even greater role for wavelet analysis, computer science, and signal processing, a 10 megabyte file could be compressed into 500 kilobytes, a manageable size to send over the phone lines, and it could be done without sacrificing fidelity. Human fingerprint experts nodded their approval. So did computers. The compressed files versus the FBI's automated identification system with flying colors. It was good news for calculus and bad news for criminals. The principle of least time. I wonder what Fermat would have thought of this use of his ideas. He himself was never especially interested in applying mathematics to the real world. He was content to do math for its own sake, but he did make one contribution to applied mathematics of lasting importance. He was the first person to deduce a law of matter from a deeper law by using calculus as a logical engine. Just as Maxwell would do with electricity and magnetism 2 centuries later, Fermat translated a hypothetical law of nature into the language of calculus, started the engine and fed the law in, and outpopped another law, a consequence of the first one. In so doing, Fermat, the accidental scientist, initiated a style of reasoning that has that has dominated theoretical science ever since. The story began in 1637 when a group of Parisian mathematicians asked Fermat for his opinion on Descartes' recent treatise on optics. Descartes had a theory about how light bends when it passed from air into water or from air into glass, an effect known as refraction. Anyone who has ever played with a magnifying glass knows that light can be bent and focused. In my youth, I liked to set leaves on fire by holding a magnifying glass over them on the driveway and lifting the glass up and down until the sun rays focused into a thick white spot of blazing intensity, causing the leaf to smolder and eventually ignite. Reflection is used in less spectacular ways in our spectacles. The lenses in our glasses bend and focus the light rays when they belong at the right place on the retina to correct faulty vision. The bending of light also explains an illusion you may have noticed while longing by a swimming pool on a sunny day. Suppose that at the bottom of pool there happens to be shiny, tragically misplaced object like a piece of jewelry. You look down through the water at the shiny object, but it's not quite where it appears to be because the light rays bouncing off it get bent as they pass from water into air on their way out of the pool. For the same reason, a spear fisherman needs to aim below the apparent position of a fish to have a chance of hitting it. Refraction phenomena like this obey a simple rule. When a ray of light passes from a thinner medium like air into a denser medium like water or glass, the ray bends toward the perpendicular to the interface between the two media. When it passes from the denser medium into a thinner one, it bends away from the perpendicular as illustrated here. In 1621, the Dutch scientist Willebert Snell sharpened this rule and made it quantitative by doing a clever experiment. By systematically changing the angle A of the coming ray and observing how the angle B of the outgoing ray changed in response, he discovered that the ratio sin A over sin B always stayed the same for a given pair of media. Here sin refers to the sine of function of trigonometry, the same sine function whose wavy graph appears in our analysis of their length. However, Snell found that the value of sin A over sin B did depend on what the two media were made of. Air and water produced one constant ratio, whereas air and glass produced another. He had no idea why the sine law worked. It just did. It was a brute fact about light. The Scots rediscovered Snell's science law and published it in his 1637 essay Dioptrics, unaware that it had been found by at least three authors before him. Snell in 1621, the English astronomer Thomas Harriot in 1602, and the Persian mathematician Abu Sa'd al-Ala ibn Sal was back in 984. The Scots had given a mechanical explanation for the sine law in which he incorrectly assumed that light moved faster in a denser medium. To Fermat, that sounded upside down and contrary to common sense. Trying to be helpful and being a naive and innocent fellow, Fermat offered what he thought were a few gentle criticisms of Descartes' theory and mailed them back to the Parisian mathematician who asked for his opinion. What Fermat didn't know was that those mathematicians were Descartes' bitter enemies. They were using Fermat for their own sinister purposes, and as any teenager could have anticipated, when Descartes had told the grapevine about Fermat's comments, he felt he was being attacked. He'd never heard of the lawyer from Toulouse. To him, Fermat was an obscure amateur working out in the countryside, something easily dismissed as another nut buzzing around his head. Over the next few years, Descartes treated Fermat condescendingly and claimed that he blundered into his results by accident. Fast forward 20 years. In 1657, after Descartes had died, Fermat was asked by a college named Marie Curie de la Chambre to revisit the old controversy about refraction. Curie's inquiry prompted Fermat to take a look at the problem himself using what he knew about optimization. Fermat had a hunch that like optimists, more precisely, he guessed that light always followed the path of least resistance between any 2 points, which he took to mean that it traveled along the fastest possible route. He could see that this principle of least time would explain why light moved in a straight line and in a uniform medium, and why, when it reflected off a mirror, its angle of incidence equaled its angle of reflection. But could the principle of least time also correctly predict how light bend when it passes from one medium into another? Would it explain the sine law of refraction? Fermat was not true. The calculation would not be easy. An infinite number of straight line paths, each bend like an elbow at the interface, could take the light from a source point in one medium to a target point in the other. Computing the minimum of all those travels Computing the minimum of all those travel times was going to be difficult, especially at the embryonic stage in the development of differential calculus. There were no tools available other than his double intersection method. Plus, he was afraid of getting the wrong answer. As he wrote to Curio, the fear of finding, after a long and difficult calculation, some irregular and fanatic proportion and my natural inclination to laziness left the matter in that state. 5 years passed, while Fermat worked on other problems, but eventually his curiosity got the better of him. In 1662, he forced himself to do the calculation. It was a dot and unpleasant, but as he hacked away, at the ticket of symbols, he started to see something. The terms began to cancel. The algebra was working, and there it was, the sine law. In the letter to Curio, Fermat called his calculation the most extraordinary, the most unforeseen, and the happiest one he had ever done. It was so surprised at such an unexpected event that I can scarcely recover from my astonishment. Fermat had applied his embryonic version of differential calculus to physics. No one had ever done that before, and in so doing, he saw that the light travels in the most efficient way, not the most direct way, but the fastest. Of all the possible paths light can take, it somehow knows or behaves as if it knows how to get from here to there as quickly as possible. This was an important early clue that calculus was somehow built into the operating system of the universe. The principle of least time was later generalized to the principle of least action, where action has a technical meaning that we did not go into here. This optimization principle, that nature behaves in the most economical way, in a certain precise sense, was found to correctly predict the law of mechanics. In the 20th century, the principle of least action was extended to general relativity and quantum mechanics and other parts of modern physics. It even made an impression on philosophy in the 17th century when Gottfried Wilhelm Leibniz argued that all is for the best in the best of all possible worlds, an optimistic point of view later parodied by Voltaire in Candide. The idea of using an optimal principle to explain physical phenomena and to deduce its consequences with calculus began with this very calculation by Fermat, the tussle over tangents. Fermat optimization techniques also allowed him to figure out tangent lines to curves. This was the problem that really made Descartes' blood boil. The word tangent comes from a Latin root for touching. The terminology is apt since instead of cutting across a curve in two places, a tangent line touches the curve at one point, barely grazing it. The condition for tangency is similar to that for a maximum or a minimum. If we intersect a curve with a line and then slide the line up or down continuously, the tangency occurs when two intersections coalesce into one. by some time in the late 1620s. Fermat was able to find a tangent line to essentially any algebraic curve, meaning a curve expressible solely in terms of whole number powers of x and y without any logarithms, sine functions, or other so-called transcendental functions in it. Using his big idea of the double intersection, he could calculate everything with his methods that we can today with derivatives. Descartes had his own method for finding tangent lines. In his geometry of 1637, he proudly announced his method to the world, and aware that Fermat had already solved the problem, Descartes independently hit on the double intersection idea, but he used cycles instead of lines to cut through the curves of interest. Near the point of tangency, a typical cycle would cut through the curve at 2 points, not at one. By adjusting the location and radius of the cycle, Descartes could force the two intersection points to merge into one. At the double intersection, bingo, the cycle intersected the curve tangentially. That gave Descartes everything he needed to find the tangent to curve. It also gave him the normal curve which lay at the right angles to the tangent along the cycle radius. His method was correct but clumsy. It generated bustle of algebra much more than Fermat's. But Descartes hadn't ever heard of Fermat yet, so in his usual cautious fashion, he presumed he had outdone everyone. As he called in geometry, I have given a general method of drawing a straight line, making right angles with a curve and at an arbitrarily chosen point upon it. And I dare say that this is not only the most useful and more general problem in geometry that I know, but even that I ever decided to know. In late 1637, when Descartes learned from his correspondence in Paris that Fermat had beaten him to the solution of the tangent problem by about 10 years, but had never forgotten around to publishing it, he was dismayed. In 1638, he studied Fermat's method, looking for holes. Oh, there were so many. Writing to an intermediary, he said, I do not even want to name him, so that he will feel less shame at the errors that I found. He challenged Fermat's logic, which, to be fair, was sketchy and poorly explained. But eventually, after several letters back and forth, with Fermat calmly trying to clarify his ideas, Descartes had to concede that his reasoning was valid. But before admitting defeat, he tried to stump Fermat by challenging him to find the tangent line to a curve defined by the cubic equation x cubed plus y cubed equals 3axy, where a was a constant. Descartes knew that he himself could not find the tangent. With his own clunky cycle method, the algebra became unmanageable. So he was confident that Fermat would not be able to find it with his line method. But Fermat was a stronger mathematician and he had a better method. He dispatched Descartes' curve without breaking a sweat, much to Descartes' chagrin. Within sight of the promised land, Fermat paved the way for calculus in its modern form. His principle of least time revealed that optimization is woven deeply into the fabric of nature. His work on analytic geometry and tangent lines blazed a trail to differential calculus that others soon followed, and his spirituality with algebra enabled him to find the areas under the certain curves that had eluded even his more illustrious predecessors. In particular, he found the area under the curve x y equal x to the n for any positive integer n, using little more than his bare hands. Others has solved the first 9 cases n equals 1, 2 until 9, but could not find a strategy that worked for all n. Fermat advance was a giant step forward for integral calculus, one that would set the stage for Victor to come. Yet, for all that, his studies still fell short of the secret that Newton and Leibniz would soon discover, the secret that revolutionized and unified the two sides of calculus. It was pity that Fermat missed it, for he came so close. The missing link was related to something he created but never recognized as crucial, something implicit in his method of maxima and tangents. It would later be called the derivative. Its applications would go far beyond curves and their tangents to include any sort of change at all.